So what we're dealing with today is called the quotient rule. We learned the product rule yesterday. We learned the power and sum and difference and constant multiple rules a few days ago. Well, it turns out there's a rule for a quotient. Don't forget that a quotient is the result of dividing. So we have learned how to differentiate A times B. Now we're going to learn how to differentiate A over B. Okay? So we're going to apply the quotient rule to determine derivatives, and we're going to continue to apply and interpret differentiation and the results of it. I haven't decided yet, and I might not decide by the end of the class, but you have a quiz in your future, and it may be tomorrow, in which case it's going to be on the quotient rule and the product rule. And it will be a relatively short quiz, a couple, like find the derivative, A, B. Or, depending on how things go today, it might be a more extensive quiz later on in the week, like Thursday or potentially Friday. We will see how it goes. But you do have a quiz in your future. So just like there is a special rule to determine the derivative of a product of functions, because the derivative with respect to x of a product of two things is not equal to the product of the derivatives, we need a special rule. You can't just willy-nilly, as my mom used to say, you can't just willy-nilly just differentiate everything. I mean, she didn't differentiate anything, but in this context, she would use the phrase willy-nilly. You can't just apply differentiation randomly to things, because sometimes it won't work. And just like the derivative of a product is not the product of the derivative, so we need a special rule, I'm telling you the derivative of a quotient is not as simple as just taking the derivative of the numerator over the derivative of the denominator. There's a special rule for that. And that's the rule. And it's more complicated. Probably isn't surprising that it's more complicated than the product rule, because division is a more specific operation. When you multiply things together, the order in which you multiply doesn't matter. But when you divide, it does. So division on some level is more involved. It's a deeper thing. This is not given to you, and if you look at this, just look at it without thinking, it's confusing, but you should be able to decipher what this is saying. This is saying the derivative with respect to x of a quotient of two functions of x is equal to the derivative of the numerator, d dx of f of x, times the denominator, g of x, minus the derivative of the denominator times the numerator over, for some reason, over the denominator squared. But ultimately it becomes that kind of rhythmic thing like with the product rule. Derivative of the top times the bottom minus top times derivative of the bottom over the bottom squared. And it is not a rule that you will set out to memorize. It's not a rule you're given, but you will memorize it. You will accidentally memorize it. So this is what it says in words. And I don't believe I have this in your notes. I'm just telling you that this is what it means. Because of this minus sign, the order in which you subtract these two terms on the top is important. Basically, what I'm telling you is when you multiply things together, A times B, A is no different than B mathematically. They are being multiplied by each other. But since A over B is different than B over A, the order of the operations here in this rule matters. It makes a difference. You know, there's a cleaner notation, even cleaner notation. Usually I don't like just the f prime without even the x, because you can't see the x. But it's sure a communicative way to express things. It takes all of this decoration off of that into something very simple. I'm going to go through the proof. If you are interested in the proof, you can watch the video of this. I'm not going to write out the proof because I want to just click through it and give you lots of time today to practice with the quotient rule, because things will get wildly different and more complicated today because of the quotient rule. Wildly is, I don't mean to scare you. I'm just saying things are going to be more challenging. So what we're going to do, what I'm going to do is let capital F of x be the original function. So what I want to do is I want to find the derivative of capital F of x, because capital F of x is a quotient. And I hope everybody knows that there's no mathematical connection between capital F of x and lowercase f of x. I'm just using another letter. And I wish people who developed calculus and all of the rules would stop doing this, but they do it anyway. I'm going to multiply both sides by g of x first. And I don't claim to have discovered this proof. I don't know. This is like the product rule. I've tried to determine who came up with this. Leibniz came up with a proof of this or discovered it, but he used infinitesimals to justify his work, which we don't know about. I'm using a different approach. And now I'm going to differentiate both sides of this. So the left-hand side is f of x at the top of the screen. Doesn't matter. I've got two lines there. Ignore the third line. I'm differentiating the left-hand side, which is f of x, and the derivative of lowercase f of x is f prime of x. And then I'm differentiating capital F of x, g of x, which I have to use the product rule to do so. So what I'm doing is, to differentiate this, I'm taking the derivative of capital F of x times g of x plus capital F of x times g prime of x, because I'm taking the derivative of the first times the second plus the first times the derivative of the second. Are you with me? Okay. And now what I'm going to do, since what I am interested in is this is what I want to know how to find, because capital F of x is f over g, so I'm really after this. Right? That's what I want to know. But f over g is capital F. So I'm working towards rearranging for capital F prime of x. And all I've done is I've subtracted capital F of x, g prime of x to the left-hand side, but then I've written it backwards. And I hope that that's not a problem for anybody. So my next step would be to divide by g of x. And this is what I get for the derivative of the quotient of lowercase f of x over g of x. But I'm defining here the derivative of the quotient in terms of capital F of x, and capital F of x was a manufactured thing. There was no capital F of x. I'm really talking about lowercase f over lowercase g. So I'm going to replace capital F of x with what you see in the top left corner of the screen. So now this becomes that. And I think if I remember right, I have this at the top of the next page. So this is where we are at. Well, I don't like complex fractions, so I'm going to multiply top and bottom by g of x. And what happens is on the top, when I multiply that g of x through, I get f prime of x times g of x minus the g of x's cancel, I get f of x g prime of x. It's a very simple proof, but you need to know the product rule to prove the quotient rule with this particular proof. That's the quotient rule. So let's get to it. I'm sorry, does anybody have any questions with that proof? Again, you will never be asked, I don't believe, in this course, in any kind of evaluation, quiz, assignment, exam, to prove something. But I am here to prepare you for post-secondary as well. Well, that's the primary thing we're here for. And if we derive some pleasure along the way, great. Get that derive? Determine the derivative of each of the following functions. This function is a really simple type of function. And this is something that I would expect you to be able to do on a quiz tomorrow if we have a quiz on what we've learned so far. It's not a difficult thing to do, but you need to know the rule. The rule is the derivative of the top, which is 3, times the bottom, which is 4 minus 5x, minus the top, which is 3x minus 2, times the derivative of the bottom, which is negative 5x, over the bottom squared. And I'm going to double check that because, again, and you're probably finding yourself in this position a lot where you get on autopilot in your writing and work. It's very easy to do. So let me just write this out so you can see. This is d top, which is not a valid notation. This is the bottom. Then we have minus, this is the top, times d bottom, which again is not a valid notation, and this is the bottom squared. So the derivative of the top is 3. I'm just running this through my head to make sure. The bottom is correct, minus the top is correct. The derivative of the bottom is not negative 5x, it's negative 5. Okay. Very common to forget to square the bottom. I mean, it's an important feature. Obviously, you need to do it, but you'd be surprised how often you forget to do that. So now we're going to simplify the top. And the top has 2 terms. And what I'm in right now in terms of a mode is algebra mode, not calculus mode, algebra mode. The top has 2 terms, so your first thing that you should do is say, is there a common factor I can factor out of the top? And the answer is no, there is not. It would be different if this was negative 51, because 51 is divisible by 3, and I could take a 3 out of the first term and a 3 out of the second. So since we can't factor anything, we have to multiply out the top to see what it becomes. Because if we do, maybe after doing that, the top is factorable where one of the factors, and it won't be, but where one of the factors is 4 minus 5x. So I expand this out, I get 12 minus 15x minus negative 5 times 3x is negative 15x, and I'm subtracting it, so it's 15x. This bit of business of the negative 15x plus 15x happens almost all of the time. Well, it will happen all of the time when you're looking at this type of quotient. Linear over linear. It's going to happen. You can sort out for yourself why it's going to happen. And then I also have the negative 5 times the negative 2, which is positive 10, but I'm subtracting it, so I get that. And this is over 4 minus 5x, quantity squared. And we're basically done. We can write 2 over 4 minus 5x, quantity squared. I might, so are we okay with that solution? Okay, I might on an exam give you this as a numerical response question where I say the derivative with respect to x of 3x minus 2 over 4 minus 5x is equal to a over b minus cx raised to the d. Because there are ways you can kind of cheat the system on your calculator, and I don't want to reveal all of them just yet, but multiple choice questions where derivatives just contain x are very rare. You know, what I mean is If they just contain x, it's something that you could probably work out on your calculator. As the derivatives get more complicated, that is certainly going to appear as multiple choice because the calculator becomes unwieldy. Any questions with the first example? All right. 2x squared minus 2x minus 12 over x minus 4. So we're going to use the quotient rule here. dy dx will be equal to the derivative of the top, which will be 4x minus 2, times the bottom, which is x minus 4, minus the top, which is 2x squared minus 2x minus 12, times the derivative of the bottom, which is 1, over the bottom or denominator squared. Double check our work, my work, your work. The derivative of the top is indeed 4x minus 2. Imagine there was a time where you had to find the derivative of 2x squared minus 2x minus 12 using limits. It's 4x minus 2. You're in agreement, I hope? Okay. Times the bottom, x minus 4 minus the top times the derivative of the bottom. It looks okay. You have to ask yourself here, is it worth it to factor? Because I've told you you should be factoring first. And the simple fact of the matter is that there is a common factor between those two terms. It's 2, right? So I could factor a 2 out of the 4x minus 2. And don't write this down. You can if you want. But I could factor that out and have left 2x minus 1 times x minus 4. And I could factor a 2 out of this and have x squared minus x minus 6 times the 1. And you have to ask yourself, if you do that, well, maybe you have to ask yourself this, do you want to do that? I mean, maybe you do. And then you're going to multiply all this out and see if there's another factor after this is cleaned up that you can take out. I'm inclined to just leave that 2 in there and take it out later with any other factors that may appear. Are you with me on the reasoning here? How many of you would take that 2 out right now? Don't let the fact that I wouldn't dissuade you from taking it out. Would anybody want to take it out? Well, I've already taken it out, so maybe let's proceed in this fashion. Okay? You could have left it in. I really want to make sure you understand. If there is some bigger factor, by all means, take it out. I don't mean bigger like 3. I mean bigger like x to the negative 1/2. Because if you do take that factor out, simplifying what is left does become easier. So let's take it out. What do I have left? Well, I have to FOIL this out. I get 2x squared minus 9x plus 4. And I have minus x squared plus x plus 6. Double check that. I'm asking you, sorry, didn't have much of an inflection in my voice there with a question. I'm asking you to double check my expansion and simplification on the top. I think it's fine. So now we can simplify the top a little bit more. 2x squared minus x squared is simply x squared minus 8x plus 10 over x minus 4 quantity squared. I'll just double check that. It looks okay. So what I was talking about earlier is if you didn't take that 2 out, then you would be looking at 2x squared minus 16x plus 20. Then you would take it out. Does 2x squared minus 8x plus 10 factor? Well, the coefficient of the quadratic term is 1. So if it does factor, you would be looking for two numbers that multiply to give 10 and add to give negative 8, and there are no two integers that do that. So are we okay with that? That's your answer. Root x minus 4 over root x plus 4. So my first step is simply to rewrite this with exponents to make it sensible for me to differentiate the top or the bottom. Now I can go ahead and apply the quotient rule. The derivative of a quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared, as is pretty much always the case. You need to get in the habit, particularly from here on in, of checking line by line your work. Don't just write stuff down that's coming out of your head without thinking about it, without stopping and reworking it. The derivative of the top is, in fact, 1/2 x to the negative 1/2, and then times the bottom, which is x to the half plus 4, minus the top times the derivative of the bottom over the bottom squared. Are we okay with that step? Can I write the bottom as x plus 16? No. The square of a sum is not the same as the sum of the squares. If you wanted to write out what x to the half plus 4 quantity squared is, you'd have to take x to the half plus 4 times x to the half plus 4 and FOIL it out and get some really awkward looking trinomial. Why would you bother? It's already factored. Now I have two things I have to take care of here. I have negative exponents that need to be factored out, and I have a complex fraction. And we're going to do both of those, but not at the same time. My experience is very few people can handle getting rid of the little mini denominators of 2's in the numerator and factoring at the same time. Your textbook will factor fractions out, and that becomes problematic later, in my opinion. Okay? We're going to get rid of the fractions first, and we're going to get rid of the fractions by simply multiplying the top and the bottom by 2. So if I multiply the top by 2, I get dy dx equals, now it just is x to the negative half, and then x to the half plus 4, minus, I also have an x to the negative half, and x to the half minus 4. So when I multiply that 2 through the first term, which is this whole thing, the 1/2 times the 2 gives us 1. And I'm left with this piece and this piece. When I multiply that whole second term by 2, the same thing happens with this 1/2 and the 2, so I'm left with this piece and this piece. I just chose to write the x to the negative half in front, so I can really visually show you that there is a common factor of x to the negative half. Could you, because the top is pretty simple in terms of if you wanted to multiply it out, could you multiply out the top and then factor? Yes, but we're in a territory here where you don't want to neglect factoring unless it's just numbers, which you can take out later. So we should factor out that x to the negative half. And we don't have to think about this. It's going to be x to the half plus 4. Well, don't have to think about it. You always want to think. But what I mean is there's no which exponents do we have. We're just taking out the x to the negative half. And then minus, of course, the x to the half minus 4, which does need to be in brackets. And this is over 2 times x to the half plus 4 quantity squared. So I'll leave up those two steps right now, allow you to finish writing that and mull over what just happened. It might help you see it better if I had a set of brackets around that x to the half plus 4. But all I've done is I've factored out x to the negative half. Now I can move that x to the negative half into the denominator, where I will write it as a positive 1/2 for an exponent. And this is going back to what I've talked about before, that you want to be able to find out when the top is equal to 0 and when the bottom of a derivative is equal to 0. You want to know when the derivative equals 0 and when the derivative is undefined. And right now I can see on the bottom that the derivative is undefined when x is 0. We're not going to do that today, but I'm saying there will come a time where it becomes important. The derivative is also undefined if root x plus 4 is equal to 0, but that will never happen because that would mean root x equals negative 4, and the principal square root of something is never negative. On the top we get 8. X to the half minus x to the half is 0. 4 minus negative 4 is 8. So now we can simplify that 8 with the 2 that we factored out earlier. So our final answer is the derivative of this function is 4 over x to the half plus 4, quantity squared. I lost my squared someplace along the way, didn't I? It was just in that second last step. So the derivative of the original function is what's at the bottom of the screen. Somebody asked yesterday, I think, about the whole exponents and the halves and square roots. Could we write this as dy dx? Could we write dy dx equals 4 over root x plus 4 quantity squared? Yeah, and you know what? I don't really think there's any difference. Well, I know there's no difference between those two, but in terms of students looking at it, you should know x to the half is root x anyway. So it's kind of like me saying yes or oui in French. If you're familiar with the conversion, it doesn't matter what I say, you understand the meaning. Any questions with that one? All right. What is the derivative of this function? Something seems a little off in how that is written. Can you confirm that that's the function in your handout? Can you tell me, is your 5 off center like that? Okay. So we're going to differentiate this. We're going to use the quotient rule. I'll go with the prime notation this time, even though I don't really care for it. So we are going to take the derivative of the top, but the top is a constant. So the derivative of the top is 0, times the bottom, minus the top, and then we need to multiply by the derivative of the bottom. But the bottom is a product. You can't just say the derivative of the bottom is 2 times 4. It doesn't work that way. You have to use the product rule. You have rules that you need to follow. So the derivative of the bottom will be the derivative of the first part of the bottom times the second part of the bottom plus the first part of the bottom times the derivative of the second part of the bottom. Are you with me? I need to apply the product rule to this product. When I find the derivative of the bottom, since the bottom is a product, I have to use the product rule. But there's another thing that becomes important here. The product rule is going to give us two terms. Derivative of the top times the, derivative of the first times the second, and then plus the first times the derivative of the second. Was I saying top and bottom a few minutes ago? Didn't think so, but I wanted to check. So because there's going to be a plus in here, I better put a set of brackets because it's 5 times the entire derivative of the bottom, which will be 2 times 4x plus 1 plus 2x minus 3 times 4. The 2 is the derivative of the first, the 4x plus 1 is the second, the 2x minus 3 is the first, the 4 is the derivative of the second. It's so easy to forget what you're doing here and to forget to divide by the bottom squared. I mean, I'm squaring 2x minus 3 times 4x plus 1. I can square them both. Because the square of a product is the same as the product of the squares. So, you know, trying to factor something like this is really not the ladder we want to climb, put it that way. Will we get there eventually, even if you could somehow wrap your head around factoring this? Yes. But I would probably start off with simplifying what this is, because then I could have two simpler terms. By the way, why would you even consider factoring? Because what's that first term equal to? It's equal to 0, right? So we have f prime of x equals 0. I'll put it in minus, because if you just neglect that first term, you might forget about this minus. And then this is 5. And I'm not really a fan of taking shortcuts because I'm always scared I'm going to make a mistake. But I think this is an okay one. Do you agree that this would be 8x and we are adding 8x? It's going to be 16x. We have 2 and we're adding negative 12. Two minus 12 is negative 10. We're, for all intents and purposes, done here. You can take out a 2 out of that factor in the numerator, and instead of writing negative 5 outside the brackets, you can put negative 10. So f prime of x is negative 10. We're taking the 2 out of here to join forces with the 5, and we get 8x minus 5 over 2x minus 3 quantity squared, 4x plus 1 quantity squared. The reason for putting it in this form, once again, and I keep saying this because I'm trying to condition you to think this way, is there will come a time where knowing the value of x that makes the derivative 0 will be important. And the value of x that makes the derivative 0 is 5/8. You don't even need to do any work. It's staring you right in the face. There will also come a time, very close to the same time, where we will want to know the value or values of x that make a derivative not defined. 3/2 and negative 1/4. And unless it's in this single fraction factors over factors form, you can't do that easily. I mean, particularly if you go back to the previous example with those roots, it's almost impossible. Any questions with any of the work for that one? All right, determine the slope of the tangent line to this curve at 2, negative 1. So you need to determine the slope of the tangent so that you can use y minus y1 equals the slope times x minus x1. So it's going to be y plus 1 equals the slope times x minus 2. So we need to determine the slope. And there's a common mistake. Are you okay with what I just said here on the left side? What's missing is the slope. There's going to be a common mistake that people make. Top of the class people make this mistake. And I'll point it out to you when the time comes. So what I need to do is find dy dx. And I'm going to use the quotient rule. The derivative of the top is 3x squared times the bottom is x minus 5 plus the top, which, minus the top. Another common mistake, because I make it from time to time, where you're using the quotient rule and you go plus instead of minus. Minus the top, which of course needs to be in brackets, times the bottom. If I were doing this on my own, I wouldn't put times the derivative of the bottom, rather. I wouldn't put times 1 because the derivative of the bottom is just 1, so who cares? And this is over the bottom squared. Now, let's simplify it just for kicks, because you do need to know how to simplify it, even though you can finish this problem without simplifying it. There is nothing to factor out of those two terms. Let me highlight the two terms so that you can see them. This is a term, and then it's minus this. There's nothing to factor out of them. The first term has a factor of 3. There's no factor of 3 in the second. The first term has a factor of x and a factor of x squared. There is not a factor of x or x squared in the second term. The first term has a factor of x minus 5. There's no factor of x minus 5. So you have to expand this out. And you're going to get 3x squared times x, which is 3x cubed, minus 15x squared, minus x cubed, minus negative 5 over x minus 5. Which can be written as dy dx equals 2x cubed minus 15x squared plus 5 over x minus 5. And I did it again. I forgot to square that. Forgot to square it way back here. And those of you that are currently in Math 30-1, that's a cubic polynomial expression on the top. I suppose we could try to simplify it and write it in factored form and see if there's a factor of x minus 5. But there isn't a factor of x minus 5, otherwise we would have been able to factor it out at top. This is not going to be factorable. Or at the very minimum, it's not factorable to give you x minus 5. Anyway, it doesn't matter, because all we're going to do is use this to find the slope. Here is the mistake that I see people make. For goodness sake, don't write this down. They write this. And then they work on simplifying this whole thing. What's wrong with that person's logic, if you want to call it that? I mean, isn't the slope the derivative? I think I've suckered some of you into believing that you should be able to do that. Does anybody know what's wrong with that? Alex? So is it at x equals 1?
Oh, sorry,
2? Okay. Should I put 2 here as well? No. The x's in my derivative means something different in this context than the x in the x minus 5. X minus 2. What I am after is the value of the slope at that point. So I have to put 2 in here first to get a numerical value for the slope. Were you going to add something to that?
I forgot to square it again.
Did I, when I wrote it down over there? Okay. Good thing I don't write the exams. So let's everybody put 2 in here and find out what we get for the slope. See if I can redeem myself here. You're probably getting negative 39 ninths.
I just haven't simplified it yet.
Yeah. The top becomes negative 39, I believe. The bottom becomes positive 9. And 39 over 9 reduces to 13 over 3. So now we're off and running. We're so close to being done. I'm going to multiply both sides by 3 to get 3y plus 3. And that leaves me with negative 13 times the x and negative 13 times the negative 2. I'm getting 13x plus 3y minus 23 is equal to 0. Well, let me double check my math. 3y plus 3, and I multiply that negative 13 into the x minus 2 and get negative 13x plus 26.